So, good morning, and today we will start a new topic. This will be on natural convective heat transfer. Whatever we did so far, the external forced convection and internal forced convection. So, most of you already have done the hydrodynamics part of it before. In fluid mechanics, you start with the Blasius boundary layer theory for the external forced convection, or the fully developed internal flows for a channel and for a duct and so on. But in this particular topic, natural convective heat transfer, definitely you would not have done this in a separate fluid mechanics course, because this is one problem where hydrodynamics and heat transfer are coupled together. So, unlike the other external flows and internal force convection, so you cannot separate the hydrodynamics from the heat transfer part in the case of natural convection, because it is basically the energy equation which drives the momentum in this case. So, from today the next the focus for the next 5 or 6 hours will be on natural convective heat transfer. So, what is the fundamental physics behind the natural convective heat transfer, or the motion, the driving force behind natural convection? We will look at the example of a simple flat plate which is aligned vertically. Okay. So, in the case of external forced convection, it does not matter whether you have a flat plate placed vertically or horizontally. Since you push the air by external means, you create a boundary layer, and we do not take into account the effect of gravity in those cases. But when we study natural convection, the effect of gravity becomes important. In fact, the buoyancy is the driving force here. So, it matters what is the orientation of the particular configuration. So, let us look at a flat plate which is oriented vertically, and we have gravity acting downwards. So, initially the ambient air is quiescent, that means there is no forced convection of anything. So, you just place the flat plate in a quiescent atmosphere, and then you heat this plate. You can either maintain a constant wall temperature or constant heat flux boundary condition, and you can heat this vertical plate. Now, naturally what happens is that the fluid layer which is in contact with this plate will be at a higher temperature compared to the ambient, since you are heating the plate. So, let us assume the temperature of the ambient to be T infinity. So, therefore, the fluid layer will be at some temperature T which will be greater than T infinity. So, now therefore, you know that the density is a function of temperature, especially very strongly for gases. So, when you look at say quiescent atmosphere, now the heated air here will therefore have a density which is different from the density somewhere outside where you have T infinity. So, the density here rho of T therefore will be less than rho at T infinity. So, that means you have a lower density air close to the hot surface. Now, the tendency of the lower density air is to naturally rise up, right. So, therefore, you will have over a period of time you will see visually a boundary layer which is actually forming and growing from the leading edge. The leading edge here is actually the bottom of the plate here all the way up. Okay. So, we will have a coordinate system x and y in such a way that x is in the direction of the along the plate and y is perpendicular to the plate. So, our origin will be starting from the bottom, this is your x, and the perpendicular coordinate is your y. Okay. So, in the case of therefore, the natural convective boundary layer, the boundary layer formation happens essentially due to a temperature difference. So, this is the starting point of the convection to happen, and because of this temperature difference, this essentially maintains a density difference between the hot air close to the plate and the ambient quiescent air outside. So, this density difference will cause the lighter air which is in contact with the plate to rise up, and therefore, a boundary layer is formed. Okay. So, now you can very clearly see that the cause for the boundary layer is essentially due to the temperature difference. So, the temperature difference is the driving potential in the case of natural convection, unlike the pressure gradient in the case of internal force convection or the external flow of air or water in the case of the external boundary layers. So, in this case you have temperature difference as the driving potential. So, this is a very important aspect of natural convection, and therefore, intuitively you should understand that the momentum and the energy equations have to be coupled in some way. So, unless the energy the information from the energy equation goes into the momentum, you cannot actually solve for the boundary layer growth. Now, you can also do the same way by reversing the temperature direction. That means, you can have a cold plate and you can have heated air. Okay. Suppose you have a plate where your T wall is less than T infinity. Okay. So, your T infinity is somewhere here and T wall is less than T infinity. So, what will be the direction of the boundary layer growth in this case? From top to bottom, because here this density will be a function of temperature which will be lower. So, this temperature is lower than T infinity, therefore, this density will be greater than rho at T infinity. So, essentially the heavier fluid has a tendency to go down, and therefore, you have a boundary layer in this case which essentially goes from top to bottom. Okay. So, now if you want to represent how the velocity and the temperature profile varies at a particular location, x location for this case. So, unlike the case of external boundary layer, where outside you have a bulk motion u infinity, in this case this is completely stationary air. So, when you want to draw the velocity profile at some location, so therefore, the velocity has to be 0 at the wall and also 0 at the edge of the boundary layer, right. So, you have 2 points where the velocity becomes 0 in this case. So, therefore, the velocity can attain a maximum somewhere within the boundary layer. Okay. So, obviously, this is quite different from the external force convection. So, where the velocity gradually increases from the plate and attains a maxima at the boundary layer. So, here you have 0 velocities both at the solid wall and at the boundary edge of the boundary layer, and therefore, it has to reach a maxima somewhere within the boundary layer. We do not know what is this location, we will find it out in the due course, and also we do not know what is the value of this maximum velocity, right. So, let us say this is your u max. In the case of external forced convection, you know that u max is equal to u infinity, but in this case we do not know that, we have to get it from the solution, right. And how will the temperature profile look in this case? So, you have the maximum temperature here and minimum temperature. So, this will be similar to your external convection, forced convection for a flat plate, right. So, the same way if you draw the velocity profile for this case, so it will be 0 at the 2 edges and then it will peak somewhere, we do not know where it peaks. And similarly, if you draw the temperature profile, so this is your plate, so you have higher temperature outside and then lower temperature close to the plate. Okay. So, this is how the velocity varies as a function of y and temperature as a function of y. Correct. So, we have demonstrated the fundamentals of the motion of convective boundary layer when you have buoyancy. in the case where we have a heated plate and a cooled plate. Now, let us try to derive the governing equations for this case. Okay. We will keep the boundary layer as the example. So, you have vertical flat plate boundary layer, natural convection, and let us try to derive the governing equation. So, let us assume that the length of this plate to be capital L. Okay. This is one of the characteristic dimensions that we will use in non-dimensionalizing the boundary layer equations. But before we go to the boundary layer equation, let us first write down what will be the Navier-Stokes equations, 2 dimensional steady state Navier-Stokes equations for the natural convective boundary layer past a vertical flat plate. So, how will the continuity equation look? What will be the continuity equation in this case? D by dx of rho u. So, unlike the external forced convection, we cannot claim that density is a constant. This is an incompressible fluid, but density is now a function of temperature, and therefore, since temperature is a function of position, so density becomes a function of space, and therefore, we cannot take rho outside the derivative. Okay. So, locally it will look like it is a compressible fluid, because the density keeps varying with different position. So, you cannot therefore directly at a first cut say that this is a incompressible approximation straight away. We cannot directly pull density outside the derivative and say it is a constant, right. However, it was shown later by Buzinesk. Okay. So, Buzinesk made the approximation that it is fairly reasonable to treat density as a constant in the continuity equation and also for the most part of the momentum equation, except in the body force term of the momentum equation. So, the body force, this is where the driving potential, the density difference emerges as a function of temperature difference. So, except for the body force term, which is the driving potential, it is reasonably good enough to approximate the density to be a constant everywhere else in the other equations or other parts of the equations, provided the temperature differences are small enough. If the temperature differences are very large, even the Buzinesk approximation will not be held valid. So, what we will do is just to start off, we will make a approximation as done by Buzinesk and therefore, try to pull density outside as a constant from the continuity equation, okay, and also the convective part of the momentum equation. So, therefore, if you write down the x momentum and y momentum and invoking the Buzinesk approximation. So, let us first write down the x momentum equation. How does the x momentum equation look? So, you have, let us keep density outside the derivative, but let us not divide it by density right away. So, rho of u du by dx plus v du by dy, this is your convective term. So, according to the Buzinesk approximation, he says both in the continuity equation and in the convective part of the convective acceleration part of the momentum equation, you can take density to be a constant. So, this is equal to, what are all the terms on the right hand side? Minus of dp by dx. So, now this is the momentum in the direction of the plate, that is in the vertical direction. So, you have dp by dx plus mu into d square u by dx square d square u by dy square, and then what else? You have the body force. So, here definitely the gravitational acceleration cannot be neglected. So, the body force is nothing but the gravitational acceleration g, which is acting downwards. So, therefore, we put a minus g, right. So, we have rho g, correct, right. So, now once again similar to the external forced convective boundary layer, if you do a scaling analysis, we can, or an order of magnitude analysis, we can show that the diffusion in the vertical direction, the diffusion in the y direction here, the y direction is the horizontal direction now, okay, Cartesian x, Cartesian y, and this is much greater than your diffusion along the length of the plate. Okay. So, this is the same conclusion that we also got from external force convection, and therefore, for the sake of simplicity we will only write the diffusion perpendicular to the plate or in the direction across the boundary layer. Okay. So, this is the most dominant direction of the viscous diffusion, right. So, therefore, we have the x momentum. Can you write down the y momentum similarly? So, can we write down the so what do we have for the convective terms in the y momentum? U dv by dx plus v dv by dy, but we do not have any v velocity in this case. We have only u velocity which is varying as a function of y, we do not have any v velocity, that is velocity perpendicular to the plate length. Okay. So, therefore, the advective term, the convective term of the y momentum equation will be 0. On the right hand side you will have pressure gradient term dP by dy, there is no diffusion of the v momentum also, and there is no body force in the y direction. Okay. So, essentially dP by dy is equal to approximately 0, very small, the others are very small. So, we can approximate it to 0. So, that means P is not a function of y, that means P is a constant along y. So, this is the same conclusion that we also got for the external forced convection. Okay. That means the pressure that you calculate outside the boundary layer, the same variation also happens inside the boundary layer. So, if you draw therefore a line here, the pressure at this point outside the boundary layer will be the same as the pressure within the boundary layer. Okay. So, that is why your dP by dy is approximately 0. So, this also says that the pressure variation that you find outside the boundary layer, that is dP by dx here, will be the same as what you have as dP by dx inside the boundary layer. So, therefore, now since we have this continuity and the x momentum equation, we do not have an additional equation for pressure. So, how do we therefore approximate dP by dx in this case? So, now therefore, we have to calculate dP by dx by writing down the momentum equation outside the boundary layer. Since we say that dP by dx can be obtained from applying it outside the boundary layer. So, outside the boundary layer these become the Euler equations. Okay. In this case there is no advection at all. So, essentially the convective term is completely 0. So, if you write the momentum equation outside the boundary layer, so you end up with minus dP by dx, and then what else? So, you do not have advection term, you do not have any diffusion term outside, there is no viscosity, and you have but body force. Okay. But we will distinguish the density within the boundary layer from outside. So, we will express the density here as rho infinity. Okay. So, outside the boundary layer we will use rho infinity here, therefore, we will write this as minus rho infinity g is equal to 0. So, this gives that my dp by minus dp by dx is equal to rho infinity times g. So, therefore, I can find my pressure gradient along the plate by applying the equation outside the boundary layer, and I determine that this is nothing but the gravitational acceleration outside. Yeah.
So, what is the logic of taking this? Why we are not taking inside?
Yeah. So, in the case that inside we do not know how the variation is, otherwise we have to solve for this, and we have to build another equation to solve for it, or we have to use the equation of state, correct. So, in order to therefore simplify it, we take it outside the boundary layer, and we see that already from momentum equation we get the clue that there is no variation of pressure along y. So, therefore, dp by dx does not matter whether you calculate inside or outside, and outside it simply is equal to the gravitational acceleration. So, if you directly substitute it, now you are eliminating dp by dx from the momentum equation. Therefore, now if you substitute for dp by dx, you have mu d square u by dy square here. So, minus dp by dx is rho infinity. So, therefore, you have rho infinity minus rho times g. So, this will be the body force. Okay. So, the effect of rho infinity g is coming from dp by dx, and the default body force is rho g. So, this difference rho infinity minus rho, what is this force? This is your buoyancy force. So, this is the net buoyancy force which is now driving the momentum in the natural convection, right. So, if the buoyancy force is 0, then you do not have any boundary layer growth. Okay. The boundary layer growth happens in this case only because of this density difference, and what is causing this density difference? Temperature difference. So, now this is where Boussinesq approximation is used, in the sense we are ignoring the variation of density as a function of temperature elsewhere except in the body force term. Okay. So, now to invoke the Boussinesq approximation, so we will define the coefficient of thermal expansion beta. Okay. So, beta is the coefficient of thermal expansion. So, this is written as minus 1 by rho d rho by dt. So, what it simply measures is the variation of density of a particular fluid with respect to temperature. Okay. So, if this coefficient is high, that means you have a potential that this fluid can expand or contract very quickly, very strongly as a function of temperature. Okay. So, the higher the value of beta indicates that the potential for this density difference can be higher. Okay. And these are usually measured as a part of the thermophysical properties, just like thermal conductivity, specific heat capacity and so on, and they are tabulated for different gases. Okay. And for ideal gas, what will be the value of beta? How do you calculate beta? If you make the ideal gas equation of state, if you put in the ideal gas equation of state into this, so it will come out simply as 1 by T. Okay. So, why we are putting a negative sign here? Because usually the density decreases as your temperature increases. Okay. So, in order to make sure that this coefficient is positive, okay, thermal expansion coefficient is positive, we put a negative sign here, alright. So, therefore, now if you apply the calculate, use a simple finite difference, okay, assuming a linear variation of density with temperature. Okay. If you want to calculate the variation from some reference temperature T infinity to actual temperature T. Okay. So, how will this look? You have minus 1 by rho minus rho infinity divided by T minus T infinity. Okay. If you assume that for small changes in temperature, we can assume a linear variation in density, okay, and therefore, we can just approximate the derivative d rho by dt as rho minus rho infinity by T minus T infinity. Now, you can therefore substitute for this buoyancy force rho infinity minus rho from this particular coefficient. So, therefore, what do you get? Rho minus rho infinity is equal to minus g beta into T minus T infinity, or rho infinity minus rho is equal to g beta T minus T infinity. So, this is basically the relation between the buoyancy force to the driving potential, which is the temperature difference. So, you can therefore substitute for rho infinity minus rho from there. So, I just take g should not be here, I am sorry. So, once you substitute into this, you have g. So, you have therefore g beta into T minus T infinity. Also there is a rho here, right. Yeah, you have rho here, okay, rho beta into T minus T infinity, right. Okay. So, therefore, now your buoyancy force is now written as a function of temperature difference. So, this is now what we call as the momentum equation invoking the Boussinesq approximation. The Boussinesq approximation says that the density can be treated as a constant in the advection part, whereas you invoke that as a function of temperature in the body force term. So, now if you divide it throughout by rho, so now this looks similar to your external forced convection boundary layer equation, except the last term, which is g beta into T minus T infinity, right. So, this is your buoyancy term or body force term. So, if your temperature difference is 0, there is no natural convection boundary layer, and therefore, the boundary layer grows because of this temperature difference. So, now you can write down the energy equation also. How does the energy equation look? So, it will be no different from your external force convective boundary layer equation, right. Q dt by dx plus V dt by dy is equal to alpha into T square T by dy square. You can neglect again heat diffusion in the x direction with respect to y, and if you also neglect the viscous dissipation, okay, we are talking about small values of Eckert numbers. So, in that case this will be your same as your external laminar forced convection past a flat plate. Okay. So, this will not change. Now, what is the major difference is the inclusion of the buoyancy term into the momentum equation. So, now you can see that unlike the other case where you solve the momentum equation first, get the velocity profile. So, this is how Blasius did. First Blasius solved the hydrodynamic part, he got the velocity profile, then Polhausen used that, then he solved the energy equation. But here the velocity profile itself is coming from the temperature. Okay. So, you cannot therefore do it in a serial sequential fashion. So, all of these has to be simultaneously coupled and solved. Now, this is where the complication comes. Okay. So, that means you cannot find a simple sequential segregated solution unlike the case of external force convection. So, you have to couple all these equations and solve them. Okay. Now, we will see in the due course of another 1 or 2 lectures, we will see how to solve these equations one after the other for different boundary conditions. But before doing that, so now that we derived the governing equations, let us try to non-dimensionalize them taking some reference parameters and see what are the non-dimensional numbers that come out. Okay. So, I request all of you to scale the all the variables here. That means, you take your position x and scale it with the length of the plate, this will be your non-dimensional x, similarly your non-dimensional y. And how do you scale velocity here? U max, because we do not have u infinity, but the complication here is we do not know what is u max a priori, right. This is happening within the boundary layer which comes out of the solution, but for the time being you do not worry about it, you just assume that u max is your reference. Okay. So, we will call this as a reference velocity u subscript r, some reference velocity. It need not be u max also, it can be any other velocity. Okay. So, some reference velocity which we do not know. Similarly, your v also. Okay. Now, we do not have pressure term explicitly, so you do not have to worry about non-dimensionalizing the pressure. And what about temperature now? So, again we introduce non-dimensional temperature theta. Okay. When we do the non-dimensionalization, let us do it assuming a constant wall temperature, so that we can write this as T minus T infinity by T wall minus T infinity. All right. So, I will give you about 5 to 10 minutes time, you please substitute this into the governing equation and find out what are the non-dimensional groups. So, I will write the final expression on the board, but you please work it out and check. So, all of you please check whether you get the same non-dimensional groups. So, is that okay? So, you have therefore 1 over Reynolds number here, okay, and you have 1 over Reynolds number times Prandtl number. Okay. So, if you define your Reynolds number now as u r into L by nu, some reference velocity times the total plate length. So, you can therefore write this as 1 over Reynolds number and this as 1 over Reynolds number times Prandtl number. Well, what about this? Now, you have an additional non-dimensional group. If you see this as no units, what is the unit of beta? Kelvin inverse. Okay. So, this entire thing will be again a non-dimensional group. Okay. Now, this represents the ratio of two forces. The numerator is nothing but the buoyancy force. Okay. Your g beta into T wall minus T infinity is nothing but the density difference, rho minus rho infinity, and the denominator is your inertial force. Okay. So, we will now define a non-dimensional number in natural convection. This is called the Grashof number. So, usually denoted as GR. Okay. This is the ratio of buoyancy force G beta into T wall minus T infinity into L cube divided by the viscous force nu square. Okay. So, this is basically the ratio of buoyancy and viscous force. So, you can imagine that this Grashof number is somewhat analogous to the Reynolds number in forced convection. So, there you have inertial force, here the inertial force is replaced by the buoyancy force, or in fact the inertia here is driven by buoyancy. Okay. And therefore, you can write this ratio of buoyancy to viscous from using the Grashof number and Reynolds number, because Grashof number is a function of buoyancy and viscous force, Reynolds number function of is nothing but inertia and viscous force. So, therefore, you can write G beta L into T wall minus T infinity by u r square. How do you express this in terms of Grashof and Reynolds number? Turns out to be that this is nothing but Grashof by Reynolds number square. Okay. So, therefore, this entire non-dimensional group is nothing but the ratio of Grashof to Reynolds number square. Okay. So, in the process we have therefore defined a new non-dimensional number which is very much relevant to natural convection, which is now called as the Grashof number, ratio of buoyancy to viscous force, analogous to the Reynolds number. Now, from this can we kind of estimate what is the order of the reference velocity? Okay. So, what is the equivalence of Grashof and Reynolds number? So, you can say that Grashof number to the power half is of the same order as the Reynolds number, correct, because we have GR by RE square. That means, the order of RE square should be of the same order as GR. Now, therefore, you can substitute the expression for Grashof number, Reynolds number, then calculate what is the order of the expression for calculating the order of U reference. Okay. So, this is nothing but G beta T wall minus T infinity L cube divided by U square to the power half which is equal to u r L by nu. So, from this what do you get for u r? So, you have L power 3 by 2 minus 1, which is L power half. Okay. So, you have nu which cancels. Therefore, u r should be square root of g beta into T wall minus T infinity into L. Okay. So, to get your reference velocity, at least the order of it, you can therefore use this particular expression. Okay. Otherwise, from your when you non dimensionalize it, you do not know what is your reference velocity, but you can now using the order of magnitude between Grashof and R e square, you can therefore come to some reasonably good estimate of reference velocity. Okay. So, you can see that this reference velocity is nothing but what is going into your Reynolds number definition, and here it is driven by your temperature difference. If there is no temperature difference, therefore, there is no inertia. Okay. The inertia is essentially arising from the buoyancy term, which is actually a function of your temperature difference. Therefore, you can classify different regimes. Now, what we have seen is a pure natural convection case, but you can also have a case where you can combine your forced convection with buoyancy. That means, you can have a regular bulk velocity, let us say this is your u infinity, and the temperature difference is also substantial. So, that you can have a boundary layer growth. Now, this is a combined effect of both your forced convection and natural convection. Okay. So, in such a case the same equations are valid, right. So, but in that case your u reference there you can actually use as u infinity, because even if you do not have any temperature difference, the forced convective boundary layer will still exist. Okay. So, when you define the Reynolds number in that case, you can define Reynolds number using u infinity, okay, which indicates the external bulk convective motion, and the Grashof number is still decided by the buoyancy ratio of buoyancy to viscous forces. Okay. So, in that case what is important, what are the different regimes and what are the how are the different regimes classified is by the ratio of Grashof by R e square. Okay. So, if you are talking about these values much lesser than 1, that means your bulk velocity is now overpowering your buoyancy force. So, in that case you can ignore natural convection, and therefore, this is only pure forced convection. So, remember in this case we define Reynolds number as u infinity L by nu, correct. So, in this case when Grashof by R e square is very small, you ignore your natural convective effects, buoyancy effects. On the other hand, if your Grashof by R e square is very large, that means your buoyancy force is dominating your bulk motion. So, here this will be your natural convection. So, by the way, the other name for natural convection is called free convection. Since you do not spend, you are not putting any effort in driving in making this convection happen, it happens naturally, and therefore, it is called free convection. So, the regions where this is significant, that is the order of 1, Okay. So, here this is called mixed convection. So, in the case of mixed convection, both the effects of forced convection and natural convection will be equally significant. You cannot completely ignore therefore either of them. So, we have already seen cases of forced convection, derived the correlations for Nusselt number and so on. Similarly, for natural convection we will do it. Now, what happens in mixed convection? Okay. So, in mixed convection the most simplest way of approaching this is the Nusselt number in mixed convection is simply calculated from independent correlations for forced convection and free convection, and we just use some power law to blend these two. Okay. So, this is one of the simplest approaches. So, here the value of m could be either 0.3 or 0.4. Okay. So, we will stop here. So, tomorrow's class we will look at the different ways of solving the governing equations. Okay. So, for first starting with the constant wall temperature case, then with the constant heat flux case and so on. Okay. Thank you.